Okay, next on the stack here, we have Nicholas Chaimov from the University of Oregon. Nicholas is a PhD candidate at the University of Oregon. He's studying performance analysis of task-based runtimes for high-performance computing and big data applications. Nicholas, come on down. Scaling Apache Spark on Lustre. Let's hear it for him.
Thank you.
Thank you.
So I would like to talk today about some work that I actually, even though I'm at the University of Oregon, that I actually did at, as you can see on the slides, Lawrence Berkeley National Laboratory with some of my colleagues there this last summer. And I also want to thank Intel for its support of this work through its Intel Parallel Computing Center. And so basically what we did with this work was we were taking Apache Spark and we want to run it on our supercomputer systems that we have at NERSC at Berkeley, Edison and Corey. And these are Cray XC systems, which are diskless. And so for storage, Lustre is basically all that we have. And when we started out, we really couldn't get scalability beyond 100 cores or so. And so we had to make some modifications to the runtime in order to work around some design issues with that. So I just wanted to start out by just sort of introducing Spark for those of you who aren't familiar with it. So Spark is a fast and general engine for large-scale data processing. And it's a specialized runtime that is sort of focused on programmer productivity in a way that a lot of high-performance computing environments are not. So this is focused on sort of trying to get performance without requiring the programmer to manually specify a lot of details about how work should be partitioned across nodes or such. And that also gives us elastic parallelism so that we can shrink and grow our work according to what resources we happen to have available right now. And it also provides automatic support for resilience so that if we have node failures, we can recover from that without the programmer actually having to do anything. And sort of in keeping with the focus on programmer productivity, it provides a number of front ends in high-level languages like Scala and Python, as well as a bunch of domain-specific libraries like Spark SQL for database applications and GraphX for graph analytics. And this was sort of developed for commodity clusters or cloud environments, not for high-performance computing system. And so it provides performance that high-performance computing people would consider satisfactory, or maybe would consider satisfactory. But when we take it and run it on these systems, we can have some issues. So Spark is part of this whole stack of software called the Berkeley Data Analytics Stack. It builds on top of a number of technologies that are borrowed from the Hadoop infrastructure. And on top of it, it has a number of technologies that make it easier to work in specific domains like graph processing and machine learning and such. And so, as I was saying, this is sort of designed for a cloud-like environment. And we want to take this and run this on our HPC system. And there are some differences in the architecture and system design that impact performance. So in our HPC system, we have a gigantic Lustre file system. Whereas if we're running on something like Amazon EC2, we have disks or virtualized disks that are local to each node, and so we have to build a distributed file system on top of that, whereas on our systems at NERSC, we already have that. However, because there are some assumptions that were made in the design of Spark that we're assuming that we have these local disks that the default configuration of Spark can give us some limited scalability in an environment like HPC, where sort of storage dominates, whereas this is intended for a network dominant environment. So I'll talk just a little bit about what's in Spark and then what file I/O actually happens in it, and then I'll talk about some of the problems that we were having. So the central abstraction in Spark is the resilient distributed data set, or the RDD. These are composed of partitions, which are composed of blocks, and you can basically think of this as a distributed list of key value pairs, except it doesn't necessarily actually contain key value pairs. What it has is either key value pairs or a lineage that specifies how you would manage to compute those when you actually need them. And so when you go to request a block, you either retrieve the value if you've already computed it, or if you haven't computed it, then you trigger computation. Just sort of as an example, here's a super simple word count thing. So we take our Spark context and we read in a text file into our RDD, and then we apply some transformations to it like flat map and map, which don't actually do any computation, they just build up this lineage. Later we call an action, collect, which reduces our data back down to a single node so that we can process it locally. That actually triggers the computation to occur. And all of the data is transparently managed by the runtime as to where it's physically located. So when we actually break this down into tasks, we take partitions from each of these, and the work associated with those gets distributed to other nodes by the runtime. And so our job is further divided into stages. And the basic idea with stages is that within a stage, there is purely partition local computation. And so this is the map stage. And then between stages is the only place where we have inter-partition data movement. Now, within the map stage, there can still be some disk I/O that happens here, which I'll explain in just a little bit, but most of the file I/O that we see happens in these shuffle stages, which is where data gets moved between partitions. So these blocks, they are ideally resident in memory, but there's a limited amount of memory we can store them in, and so if they're cached, we will evict them or spill them to disk depending on configuration as necessary. And then when we request one, if it's on disk, we bring it back in. If it's remote, we go over the network. And so this is basically the responsibility of this block manager here to manage storage in memory, manage storage in disk, and to perform network operations. And so as a result of this design, I/O sort of happens everywhere in the Spark runtime. So we have program input-output. These are things at the beginning of stage 1 and stage 2 here, where we're reading in input. And this is, in Spark, expected to be distributed in something like HDFS. So we have a bunch of nodes that have local disk and have HDFS on top of them. And then there are some runtime managed things. The block manager, for example, which can happen in any of the stages. This is where if we have to evict data onto disk, the block manager does this. And then there's the shuffle manager. And these are writing into storage that they expect to be local. They're just using a Java file output stream directly onto the local file system. And that's where we can get into some trouble. So design assumptions. Spark expects that we have a local disk with HDFS overlay for our distributed file system, and that's where our bulk storage goes. That's where our input comes from. That's where our output goes to. It also assumes a fast local disk, like preferably an SSD for shuffle files. And it assumes that these disk operations are going to be fast, because the environment that we are expected to be operating in, we're expecting an environment where we have disk I/O that's optimized for latency, and a network optimized for bandwidth. But we're going to a system where we have disk I/O optimized for bandwidth and network optimized for latency. So we did some evaluations at NERSC on Edison, which is our Cray XC40, and Cori, which is our Cray XC40. New experimental system, which also has some experimental burst buffer nodes on it. And these were all running Spark 1.5.0. So when we just went and started looking at this, we were looking at single node performance, and we had issue, even with single node, we were looking at same concurrency, this giant multi-$100 million supercomputer on a single node being considerably slower than the workstation under my desk, provided that the data was on the disk. If I omitted disk stuff, if I preloaded it into memory and used all the cores, then I would actually get performance that matched the workstation, but that's not what I'm looking for. And so I did a bunch of instrumentation on the Spark runtime to try and figure out where is the time going. And what I ended up discovering is that the time seemed to actually be going into file open operations. The biggest difference between the workstation and the local disk was in time per file open, where individual file opens were taking on the mean 23 times greater time on Edison than on the workstation. But that wasn't really the problem. The problem was the incredible variability that we were seeing, where the worst case file open time was 14,000 times greater on Edison than it was on the workstation. And so then we tried to look into this and say, okay, well, we know metadata operations aren't the greatest, but what's going on here? Why is this so bad? And what it turns out is that during this shuffle phase, Spark is designed so that the number of shuffle opens is equal to the number of shuffle reads. And so what this basically means is that the Spark is trying to maintain sort of functional semantics for its tasks, so that a task, when it finishes, is supposed to leave the system in approximately the same state that it was when it left, which means if it opens a file, well, it should close it so that it's not interfering with anything else. So, and then during this shuffle phase, we have each of the map tasks on the local side of the shuffle. They open a file and they write a partition to it, and then they close it, and then they open it again, and they write another partition, and they close it, and they do this for as many times as there are partitions, for as many files as there are partitions. And the number of files that there are is, the number of partitions that there are, which is equal to the number of files that there are, is proportional to the number of cores that you have. Basically, you need to provide enough partitions that there's enough work for the number of cores, and then you really want to provide even more so that you can have latency hiding kind of things. So this is a problem because that means that the number of file opens that we are doing is proportional to order number of cores squared. So as we are increasing the number of nodes, the blue line here is the amount of time that we're spending per operation in an open, and that's going up as we are adding nodes at the same time as the number of opens is going up with the square of the number of nodes, so that by the time that we have 16 nodes here in this test is basically a worst case shuffle. It's a group by, you have a bunch of data with keys and values, and then you want to bring all the values associated with the key together. So this is basically a micro benchmark of worst case shuffle. At something really small, like 16 nodes, we already have 2.35 million file opens that we're doing, and that is bad. Yeah, and so the time per open increases with scale, unlike with the read and write. And so we need to eliminate these file operations that affect the metadata server, because these are almost single-handedly killing our performance on this system. So the main things that we look at is, well, can we say, I don't care that Spark is supposed to have functional semantics, I'm just going to keep these files open throughout the entire shuffle thing. So basically, can we cache the file descriptors? What some developers at Cray did was they just said, well, we'll just use a memory mapped local file system, which is not a scalable solution because when Spark runs out of storage, it just aborts the job. And that is a small file system. And then the other thing is that we looked at is using basically a loopback file system backed by a single Lustre file, which actually works really well, but there is some engineering work required to actually let users on the systems do that without being root, which we don't want them to be. So I also want to say just that these are all sort of partial solutions because not all of the problems strictly come from Spark. So for example, there's a number of file format readers that do a bunch of redundant opens. So the Parquet reader, for example, it likes to open a partition file and a checksum file, calculate the checksum, read the checksum, compare them, then close the file, open it again, read the footer, close the file, open it again, and read the rest of the documentation. So these problems can be sort of spread out throughout the ecosystem. So there can be issues where these third-party layers are not optimized for this. So with our file pooling approach, we just have basically a pool in the JVM of file stream objects, and when we want to open a file, we instead borrow it. When we close the file, we flush it and return it to the pool. And if the pool's full, then we close the least recently used idle stream. We can do this largely because there's no distributed information needed, because these files are all expected to be on a local disk, so these aren't shared. This takes us from order n squared to order n file opens, and we can bound the size of the pool by sort of statically looking at how many partitions are there and how many reader threads do we have operating on them. But we still need to limit the size of the pool because we have to let the JVM and other parts of Spark have some open files. This works, but with some caveats. And so with our loopback file system approach, we have this system at NERSC called Shifter, which is a lightweight container infrastructure for HPC, which is similar to, but is not Docker. But it is compatible with Docker images. And this is integrated with our scheduler so that when you submit a job to our batch system, you can say that you have some Docker image that you want to work on. And this already had the capability of mounting loopback file systems because we needed read-only loopback file systems for the images. So it was possible to basically add a per node loopback file system capability for here so that when we're submitting a job to the scheduler, we can say that, well, stored on the Lustre file system, I want a per node cache of some size, and that will be created for each node in the job and then mounted within the context of the container running on there. And so that allows us to have just a single file open with intermediate data files kept open. So this is performance results for, again, that sort of worst case shuffle. So this is like the limiting factor in a Spark computation is if we have a case where we have everyone having to communicate with everyone. So our file pooling alone improves our performance by 30%. This is just on a single node. And then our local mount ends up being as fast as RAM disk and is 42% faster with the file pooling plus using the mounted file. But then the big difference happens when we start scaling up. If we get to the point where we have 4 times 2,560 squared file opens, we just ruin the performance for ourselves and probably everyone else on the system, which makes everyone else mad. So with Spark on just plain Lustre, we couldn't really get any reasonable scalability beyond 100 cores or so. With mounted file support through Shifter running inside these Shifter images, we can scale easily up to 10,000 and more cores. And then at 10,240 cores, the mounted file backed on Lustre is only about 1.6 times slower than just using the RAM disk, but we don't have the issue that, well, we're contending for RAM that the Spark application is already using, and if we run out of it, then the whole system's going to abort. We also did a little bit of looking into the experimental burst buffer on Cori, and we found that the performance penalty for with the burst buffer is a lot less than just using plain Lustre. And that's interesting because we also found that the actual median open time is actually higher on the burst buffer than on Lustre, but that ends up just being because the variance is a lot lower. So our worst case open time ends up being a lot less, so we have fewer sort of straggler tasks. And so sort of to conclude, when we tried to deploy Spark on our systems at NERSC that have diskless compute nodes with only a Lustre file system for storage, we found that the very high rate of metadata operations in Spark severely constrained our scalability. And we have implemented some solutions, some of which require changes to the Spark code, some of which don't, that improves scalability up to tens of thousands of cores on our systems. And then NERSC and Cray are already using our solutions. The file mounting stuff is built into Shifter and is available for production use on NERSC systems currently. And so I just want to acknowledge Intel for supporting this work and additional work that we're currently doing into sections of the Spark file IO other than the shuffle phase, which was just sort of really low-hanging fruit. And we also want to acknowledge NERSC for the use of their systems and their work in developing Shifter. So thank you, and if you have any questions, I'd be happy to answer them.
Andres?
So are you, well, I guess, hey, are you going to talk to Oak Ridge about Docker and the things that, and are you going to push your changes to Spark upstream so that other people get the benefit of this work?
We may do that. There have been several previous attempts to push sort of solutions to the lots of file open problems into Spark that were rejected on the basis that they were not of very wide importance. There are various like memory-only shuffles and stuff that were proposed but rejected, but that's certainly something that we're looking into. As for the Oak Ridge stuff with Docker, I had never heard of that before, so yes, I would like to talk to them.
Others? Okay. Nicholas, thank you.
Thank you.